Welcome to this next video in the playlist on field theory. In this video, what we're going to talk about is separable polynomials over a field of characteristic 0. Okay, so we are going to restrict our attention down to a field which has characteristic 0. Okay, so the field that we are working with throughout this video is going to be one of characteristic 0. So the characteristic of the field f is going to equal 0. Now remember what that means. The characteristic, remember, of a field is the smallest number of times that you must add the multiplicative identity in the field together with itself to get the additive identity as the answer. And if it's the case for the field that no matter how many times you add the multiplicative identity to itself, you never ever get the additive identity back as an answer, then we say that the field has characteristic 0. And of course some of our favourite fields, some of the most notable fields, are of characteristic 0. So for instance the rational numbers, the real numbers, the complex numbers, some of the most famous fields, they are all of characteristic 0. Add 1 to itself however many times you like in those fields, you will never ever get the answer 0 back. Okay, so we're going to be limiting our attention now just to fields of characteristic 0, not fields that have characteristic a prime natural number. And I will emphasize why we need to make that restriction throughout the video. Okay, so what are we actually going to be discussing about these fields then? We're going to be discussing which polynomials in the ring of polynomials over these fields of characteristic 0 are actually separable polynomials. So in the previous video in the playlist on field theory, we discussed separable polynomials, and we defined a separable polynomial to be one where if you construct the splitting field for that separable polynomial, in the splitting field, the separable polynomial will have all simple roots, i.e. all roots of multiplicity 1, i.e. it won't have any roots which are repeated and have multiplicity greater than 1. Okay, so what we're going to do now is we're going to be able to characterize polynomials that are separable in the ring of polynomials over a field of characteristic 0. That's the aim for this video. I want to be able to say which polynomials in this ring of polynomials over a field of characteristic 0 are actually separable polynomials. Now, by the end of the previous video on separable polynomials, we had concocted a condition, okay, which worked in an arbitrary field. We said that a polynomial would be separable in the ring of polynomials over the field capital F if it was relatively prime to its derivative. What we're going to do is get a better condition in this video, but it will only now refer to fields of characteristic 0. It won't be applicable to all fields. Okay, so we get a better, easier condition to understand by the end of this video, but as I say, it will lose its generality that condition that we had from the previous video had. Okay, so it's a condition that's now only going to apply for polynomials over a field of characteristic 0. So we're going to have two main theorems of this video. So the video is going to be divided into two main parts. Theorem 1 is going to be a sort of prerequisite to Theorem 2, and Theorem 2 is then going to be the main characterization, the main theorem, which tells you exactly which polynomials in this ring of polynomials over the field of characteristic 0 are separable and which are not. Okay, so we will begin then now with Theorem 1. Okay, so I'll give it its title. We'll call this Theorem 1, and then we'll have a break and then do Theorem 2. So, Theorem 1 then. What is Theorem 1? Theorem 1 is that all polynomials that are in the ring of polynomials over this field of characteristic 0 that are reducible, not reducible, the exact opposites, are irreducible, are going to be separable polynomials. Okay, so I'll write this down. If the polynomial p of x is irreducible, okay, and I'll remind you of exactly what irreducible means in a moment, okay, then the claim is, then it is separable. So I'll put this line here. Then it is separable in the ring of polynomials over the field f. Okay, separable over f. Right, so let's just remind ourselves firstly of what it means for the polynomial p of x to be irreducible, and then what we'll do is prove that if it is the case that it is irreducible, then we can prove that it is separable. Okay, so what does it mean to say that the polynomial p of x is irreducible? Well, remember, irreducible has two parts. Firstly, irreducible, this adjective, irreducible, it's only applicable to polynomials that are not equal to the zero polynomial and which are not units. Now remember, that basically gets rid of all the constant polynomials, because one of the constant polynomials is the zero polynomial, and all the other constant polynomials are going to be units in a ring of polynomials over a field. Okay, because remember, the constant polynomials are effectively the original field sitting within the ring of polynomials, and therefore all of those non-zero constant polynomials are going to have multiplicative inverses exactly like they did in the field capital F. Okay, so what we can say instantly is that this implies that p of x is a non-constant polynomial. It's important to remember that that's part of the definition of irreducible. In addition, of course, the bit that everyone always does remember is that it means that if you can write this polynomial p of x as a product of two other polynomials, so say you've got an equation of this form, p of x is equal to one polynomial a of x times another polynomial b of x, where of course both of these polynomials, a of x and b of x here, are going to be in the ring of polynomials over the field capital F. And of course you should say p of x is irreducible, and I should have the in f of x, because of course it means nothing just to say that some symbol is irreducible. You have to say irreducible in which ring, so it's irreducible in the ring of polynomials over the field capital F. Okay, and here is the main criterion, that if you can write p of x as a product of two other polynomials that are in the ring of polynomials over the field, then the only way that you can do this, if you find products of this form, these products are rather trivial, okay, if indeed the polynomial is irreducible. It means that these products are going to be a unit times an associate of the polynomial. The only products that you can find of polynomials from the ring of polynomials over the field, if the polynomial is equal to an irreducible polynomial, will be products of a unit times an associate. Okay, so we might say that a of x is going to be a unit, i.e. it's going to be a non-zero constant polynomial, and b of x is then just going to be an associate of p of x, and that means just p of x multiplied by a unit, i.e. p of x multiplied by a constant polynomial, if we're talking in the ring of polynomials over the field capital F. Okay, so if p of x is irreducible, then it means that the only products that you can find in the ring of polynomials which will make this polynomial p of x are these trivial ones, where one of the polynomials has to be a non-zero constant polynomial and the other is just a unit unit times p of x, i.e. an associate of p of x. So there are only these trivial products that make p of x if indeed it is irreducible. Okay, so that's a reminder of what it means for p of x to be irreducible. The claim is now that if indeed this polynomial is irreducible in the ring of polynomials over the field capital F, then you can instantly conclude that it's separable. Now, how are we going to prove that? Well, let's actually see the proof now. So, here comes the proof. Okay, so I've already mentioned that in the previous video on separable polynomials, we proved that a polynomial is going to be separable in an arbitrary ring of polynomials over a field capital F, if and only if it is the case that it and its derivative are relatively prime in the ring of polynomials over the field capital F. So what we want to now consider is the derivative of this polynomial p of x. Now, let me just write p of x out explicitly. So p of x, we know that it is a non-constant polynomial, and the key thing there is that its degree is going to be greater than or equal to 1, and that really is important here. Okay, so if I write p of x out explicitly, then it's going to look something like this: p0 plus p1x. Now, of course, that might be it. It might just end there, but more generally, it might go up to, let's say, pn x to the n here. So let's say the derivative of p of x here is equal to n, and all we can say about n is that this is strictly greater than 0. Okay, so it's some natural number that is strictly greater than 0, greater than or equal to 1. Okay, so that will become extremely important in just a moment. So now let's consider taking the derivative of this polynomial. Okay, so we'll now take the derivative of the polynomial p of x, and of course we will just use our normal rule that we defined in the previous video on separable polynomials. Okay, so the constant term will go, then we'll take the degree 1 coefficient, and that will become our constant coefficient, etc. And for all the other ones, we'll lower the power by 1 and multiply by the old power, so up to this final one here, where we'll get n times pn x to the n minus 1. And remember, when we multiply n by pn, the reason we can do that is, of course, you view n as now being the natural number in the field. You view it as meaning 1 plus 1 plus 1 n times. Okay, so all natural numbers can be viewed as being in the field. And this is one of the key things that we need. Well, this is the key reason that we need our field to be characteristic 0. If we are working in a field of characteristic 0, then we can guarantee that all of the natural numbers in the field, i.e. 1 plus itself, a natural number of times, is always not going to be 0. That's so important. If we were working in a field of characteristic a prime natural number, then we wouldn't be able to guarantee, well, indeed, it wouldn't be true to say that all of the natural numbers are non-zero. Okay, that is why we want it to be a field of characteristic 0. And why is all of the natural numbers not being equal to 0 so important? Well, it means that the derivatives are all very sensible. Okay, because look, when we multiply n times pn here, we can guarantee that this coefficient is going to be non-zero, because n is not going to be equal to 0 because we're working in a field of characteristic 0. Okay, and pn was supposedly not 0, otherwise it wouldn't have been the leading coefficient. Pn minus 1 would have been. So we're multiplying two non-zero elements together, and of course we know all fields are integral domains, so when we multiply two non-zero elements together we get something that's non-zero. So what being in over a field of characteristic 0 allows us to conclude is that the degree of the derivative of p of x is equal to n minus 1. That's a statement that you cannot say if you're working in a field of characteristic a prime natural number necessarily. Okay, I would not be able to conclude this. If we're working in a field of characteristic 0, then derivatives behave very sensibly. Okay, the degree of the derivative is just 1 minus the degree of the original polynomial, whereas that's not true if you're working in a more general field. And that's the key to why I need the condition that we are working in the field of characteristic 0. As you'll see, this is the key to the proof. Okay, the other thing I can say, well, from this, what I can now say is that the derivative of the polynomial is not equal to 0, and here's the key line. This is not equal to 0. Now, why is that? Well, we know that the original polynomial was degree 1 or greater. Now, when you differentiate a polynomial of degree 1 or greater, you do not get the 0 polynomial, because at the very least you're going to have a degree 1 term, and that will give you a non-zero constant term. Okay, so you will not get the 0 polynomial, basically. Okay, and that's the key thing that we would not be able to say if we weren't working in a field of characteristic 0, because remember from the previous video where we introduced the concept of the derivative of a polynomial, that if you're taking derivatives of polynomials over fields of characteristic prime natural number, things can work very oddly. Polynomials that you would expect to have a non-zero derivative end up having a 0 derivative, if it's the case that all of the coefficients that are non-zero are in front of powers of x that are a multiple of the prime p, which the field is characteristic equal to. Okay, so that's why we want the field to have characteristic 0, so that we can conclude that the derivative of this irreducible polynomial is not equal to 0. That's the key to all of this. Okay, I will re-stress the importance of the field being characteristic 0 right at the end once we've completed the argument. Okay, but that's a hint as to it at the moment. Okay, so now what we're going to show is that the derivative of the polynomial and the polynomial are going to be relatively prime in the ring of polynomials over the field f. And of course, if we've shown that they're relatively prime, then we can conclude that the polynomial p of x is separable from the theorem that we had at the end of the previous video. Okay, so we'll be done. So why then can I argue that the derivative of this polynomial and the polynomial are relatively prime in the ring of polynomials over the field capital F? Well, what does it mean to be relatively prime? Okay, two polynomials are going to be relatively prime if the only common divisors that they have, the only polynomial that is a common divisor of both of them, and I might call this polynomial d of x here. Okay, this is going to be the common divisor of both of them. If the only common divisor of both polynomials is a unit, okay, that's what it means for them to be relatively prime. If the only common divisor is a unit, i.e. d of x has to be a unit, then you can conclude that they're relatively prime. If there is some common divisor that is a non-unit, i.e. a polynomial of degree greater than 0, i.e. 1 or above, then they would not be relatively prime. So why can we conclude that the only common divisor of, or common divisors of both of these polynomials here are going to be units? Okay, well now we have to remember the fact that this was an irreducible polynomial. So that means that the only divisors of this polynomial, full stop, are going to be units and associates of p of x. So remember, divisors are just things that you can multiply by another polynomial to make the polynomial of interest. So divisor of this would be something that you can multiply by another polynomial to make p of x. Okay, we've shown that any product, well, we've said that the polynomial is irreducible. That was the starting assumption, that p of x was an irreducible polynomial, and therefore the only products which can make it are these trivial products where you've got a unit multiplied by an associate. So the only divisors of an irreducible polynomial are going to be units and associates of p of x. Okay, now we are looking to try and disprove these two being relatively prime. We are trying to find some divisor that is not a unit. So we're not interested in divisors which are units. They're useless to us if we're trying to disprove these two being relatively prime. So we're only interested in associates of p of x. Okay, so if we could find a common divisor of these two that wasn't a unit, then it would have to be an associate of p of x, because p of x is irreducible. Okay, so now we turn to the derivative of p of x and we ask, is there any chance at all that an associate of p of x is going to be a divisor of the derivative of p of x? And of course the answer is no. And the reason is that an associate of p of x is just a unit times p of x, i.e. a non-zero constant polynomial times p of x, i.e. the degree of an associate of p of x will be the same as the degree of p of x itself. It will have degree equal to n. Okay? Is the derivative of this polynomial, which has degree n minus 1, possibly going to be a multiple of a polynomial of degree n? Well, the answer is no. But it's really important that I know that the derivative is not equal to 0, because if there was a chance that the derivative was equal to 0, then the answer would be yes, because 0 is a multiple of anything. It's just, you could take an associate of p of x, multiply it by 0, and you'd get the 0 polynomial. That's why it is so important that we know that the derivative of p of x is not equal to 0. Okay, we would not be able to make this argument if we were working in a field of characteristic p, because we wouldn't know that the derivative of the polynomial wasn't equal to 0. But we know that the derivative of the polynomial is not equal to the 0 polynomial, and that it has degree strictly less than the degree of this one. And we know that when we multiply two polynomials together, the degree always goes up, provided that one of them isn't the 0 polynomial. Okay, so if you're not making the 0 polynomial, and you're not, because the derivative is not equal to the 0 polynomial, then the product that you're taking to make the derivative of p of x must be two non-zero things, so it would have to be an associate of p of x times something else, and no such product is going to make the degree of this polynomial suddenly go down to n minus 1, okay, because we're working in a ring of polynomials over a field, and whenever you're working with a ring of polynomials over an integral domain even, it doesn't necessarily need to be a field, we know that the degree of the product of two polynomials is just the degree of the two polynomials added together. So you take the degree of the first polynomial plus the degree of the second polynomial, and that will give you the degree afterwards. So the degree only ever goes up, except for that silly case where you're multiplying polynomials by 0, but we know we're not in this case. Okay, so all of that ramble was just to say that you can be absolutely sure that no associate of p of x is going to be a divisor of the derivative of p of x, okay, and therefore you can conclude that the only common divisors are going to be units, okay, because the only other divisors, full stop, of p of x are units, so there can't be any other common divisors of these two other than units, and therefore you can conclude that these two are relatively prime in the ring of polynomials over the field, and hence you can conclude that p of x is separable. So indeed the theorem is shown to be true. If p of x is irreducible, then we have now proven that indeed it will be separable. Okay, so I promised to re-stress the importance of the fact that the field was characteristic 0. So the entire argument hinged on us being able to show that the polynomial p of x, which was irreducible, was relatively prime to its derivative. And being able to show that it was relatively prime to its derivative relied on this formula and this statement here, that the derivative had degree n minus 1, one less than the degree of the original polynomial, and that the derivative was not equal to 0. This is where it fails if you're working in a more general field. If you're working in a field that could have characteristic equal to a prime, then you can't guarantee that the derivative of the polynomial doesn't end up being equal to 0. Okay, you can't guarantee that. And then, if you were asking, is this polynomial relatively prime to 0, of course the answer is no, because you can take an associate of p of x, and of course p of x has an associate of itself as a divisor, and 0 will also have that as a divisor, because 0 times that associate will make 0, because 0 is effectively a multiple of anything. Okay, so you wouldn't be able to conclude that the two were relatively prime, and therefore you wouldn't be able to conclude that p of x was separable. Okay, so that's where this argument fails if you're working in a more general field. So you do require the characteristic of the field to be equal to 0 so that you can conclude that derivatives are very sensible and that the derivative of this irreducible polynomial is not going to be equal to 0. Okay, so there's theorem 1 complete, and this in itself, tells us a whole bunch of polynomials in the ring of polynomials over the field that are indeed separable. If you've got any irreducible polynomial, you can conclude instantly that it's separable, and that's very nice to know. We're going to take this further with theorem 2 in the next video, but we'll have a break before that.